I'm Malinga, this is Yasanka doing this innovation session on behalf of data analytics team. So before I start the session, I would like to share a small story with you, a real life experience. So one evening, me and my team was hungry and we thought of going out and getting some pizza. So there, we had some requirements. So pizza has to be cheap, that means large pizza should be around 1,500 and the place should be nearby. It should be in 500 meters radius. So there was this kind of requirements, and some people say it is great to have Wi-Fi, and some said that if there is a discount it will be great. So as DB team we have some access to some interesting DBs, and there is one which has all the pizza stores that sells pizza. And I went ahead and write a SQL query to query this DB and give us the ideal place that we should go. So this is the query. So I was very solid when I write those requirement part, where I have to capture pizza under 1,500 within 500 meters. But when it get to that optional things, that nice to have things like Wi-Fi and discount, I really didn't know the correct way to capture that using SQL. So what I did was just do all the by with Wi-Fi and hash discount. But I knew that is not the ideal way, but that's what I had. And before running this query, I showed it to my team, and a couple of our QA guys found some usability issues. They say, of data analytics team. So before I start the session, I would like to share a small story with you, a real life experience. So one evening, me and my team was hungry and we thought of going out and getting some pizza. So there, we had some requirements. So pizza has to be cheap, that means large pizza should be around 1,500 and the place should be nearby. It should be in 500 meters radius. So there was this kind of requirements, and some people say it is great to have Wi-Fi, and some said that if there is a discount it will be great. So as DB team we have some access to some interesting DBs, and there is one which has all the pizza stores that sells pizza, and I went ahead and write a SQL query to query this DB and give us the ideal place that we should go. So this is the query. So I was very solid when I write those requirement part, where I have to capture pizza under 1,500 within 500 meters. But when it get to that optional things, that nice to have things like Wi-Fi and discount, I really didn't know the correct way to capture that using SQL. So what I did was just do all the by with Wi-Fi and hash discount. But I knew that is not the ideal way, but that's what I had. And before running this query, I showed it to my team, and a couple of our QA guys found some usability issues. They say, what if there is a great place just after 500 meters with discount and Wi-Fi and everything, and what if there is a place with 1,501 rupees with a great discount? So there was some problems. My query will just filter them out. So as what we have is this, we have to run them. So we have to eat pizza today. So I want to say that we have to add some new indexes to match the filtering parameters. So I added some new indexes and ran the query. And a couple of hours later, query was still running, and I looked around and no one was there. Everyone has went home. So that day was a very sad day. We couldn't eat pizza. So I thought of finding a new tool that would meet our requirement, and I found ElasticSearch. So going through the ElasticSearch documentation, I found something called the Boolean query. I don't want you to understand what is in here, but it's something like this. It consists of three parts, where I have to mention the must not, and should. Must is where I include that hard requirements, where I should capture, and the should part is therefore that nice to have things, and I don't need the must not part in here. So one of my problems was solved. So we can query with saying that it is nice to have Wi-Fi. And going through the documentation, I found something called Gaussian function, which helped me to get that second problem out of our hands. So here we just filtered those nice two restaurants, but with the Gaussian function, I can ask ElasticSearch to the exact query within the 500-meter radius part, but search for the full data set with some kind of decay to the scope. So it will include all the restaurants, but it will reduce the marks when it gets away from the 500-meter boundary. So both of my problems were solved. So what I want to tell you is, nowadays when the people are searching, they want their emotions to be searched. So they are giving some approximate queries, thinking that search engine will give them approximate answers. They think that their spelling mistake will be forgiven. And people need a smart search, something beyond the simple full text search. So let's start the presentation. So in this presentation, we will talk about, give a small introduction to ElasticSearch and do a basic comparison between Solr and ElasticSearch. What is Solr? It is something like ElasticSearch. We will get to it later. And we will talk about Lucene, which is the base for both Solr and ElasticSearch. And people who know about the history of Solr and Lucene, they might say it is not the base, but let's make it simple. And it is the base for both Solr and ElasticSearch. And we will show you some demos and some use cases we found in the Leapset where people have used ElasticSearch. ElasticSearch provides much easier APIs that people can understand. And if you take pure Lucene, it supports Java, but the children of it supports a lot of programming languages. And there is very limited capabilities when it comes to clustering and replication with Lucene. And if you take Solr and ElasticSearch, they provide very good defaults for very complex Lucene classes. Let's go for their children. So if you take Solr and ElasticSearch, as you can see, they are both from the same family. So there are a lot of similarities. If you take, both can do full text search and both can process structured and unstructured data. Both can do queries, filters, caches, and facets. So if you talk about faceting means it's about aggregate statistics. So think you are querying a movie database and you make a simple query to get all the movies, but you want to aggregate them, get the aggregate counts for each category. So it is a query something like that, and it will give the counts for each category. And both of these tools are cloud ready. And talking about the differences, let's start with the download size. Solr is much bulkier than ElasticSearch, but we can't call it a waste because Solr provides much more facilities than ElasticSearch. ElasticSearch, on the other hand, based on plugins. We can install the base package and install plugins on it, but it will eventually become bulky as same as Solr when you install plugins on that. If you take the distributed coordination, Solr uses zookeeper, whereas ElasticSearch uses its own algorithm. According to community, they are satisfied with the Solr's zookeeper because it is more mature and it's very well known for that purpose. But ES is rapidly developing in this area. And if you take a release process, Apache Solr uses the full Apache release process, where you have to wait for some time to get the release out. But if you take Elasticsearch, it use something called LGTM, where this looks good to me. If it looks good to the product owner, they do the release. And ElasticSearch talk about magic. They say that do not change our default configuration. It do work in 90% of the time. Just use this and you will see the magic. Whereas there are a lot of configurations in Solar and you can optimize with that configuration. If you are a person who like to configure and optimize your things, Solar is the answer. And if you are a person who want to get the things done and do minimum set of configuration, ElasticSearch will suit you. So of ElasticSearch, which is Lucene. Here I want to show you when you are given some kind of document, how it get indexed. Here I have given HTML document, and first it goes through character filters. So there are a couple of character filters that we can use in ElasticSearch. Here I have used HTML stripper, where it will strip out the HTML tags and get the content out. Then it goes through the tokenizer. There are several tokenizers. Here I have used standard tokenizer, which is the standard for European language tokenizing, which will tokenize the words according to some grammar rules. And here I have used several token filters, actually two. There are a lot of token filters in ElasticSearch, and you can use as much as you like. Here I use the stop word tokenizer, where you will remove the stop words like the, a, like that. And there is another token filter to make everything lowercase, so there won't be any difference between the capital J jump and simple J jump. And after I have this set of tokens, I'll go for the indexing. So after indexing, what I will get is the inverted index.
Let's move with the nice part, and of course those are nice too. But if you are just wondering how you can play with this beast, ElasticSearch is just a zip file that you can download and unzip it. And just run this script inside it, and in your local host and local machine you can have a ElasticSearch node right instance away. But in production you won't end up in a single node, but to add more and more nodes to cater your load. So here we can just add 3 nodes here for the demonstration. ElasticSearch provides this parameter level configuration that you can just start the ElasticSearch search nodes. So here the node is consist of shards. Shard is a basic scaling unit where in distributed systems sharding is very much popular to partition your data. And sharding, each node consists of 2 or more shards, and shard is spread among the cluster where the primary and replica are maintained for the high availability reason. And ElasticSearch index is composed by these shards, and shard is a Lucene index, but Malinga mentioned earlier, and a Lucene index is a composed of segments called inverted index. So the basic architecture or the storage architecture is just summarized in this slide, and the inverted index is used to traverse or the search through the documents that we need to access. So here in our production cluster, we tweak some performance of the ElasticSearch cluster, where the Lucene index, when the documents keep growing, the index of the Lucene will keep growing. So eventually, in a occasion time, the segments are merged, but instead, since ElasticSearch is an in-memory searching platform, all the caches or all the inverted index keep in the cache or the operating system pages until they are flushed or committed to a persistent storage. But the most important of the magic here is the segments are immutable, so you cannot delete these segments even if you want. What they are doing is, if you want to delete a document, you just flip a bit from the main index, so the inverted index or the segments cannot be accessed from the main end. So, and for each nodes, they have data nodes, master nodes, and client nodes. For every node, they know the cluster state by keeping the index mappings and the shard routing tables for routing the request among the cluster, and the nodes metadata where the nodes is running and which zone it's running. So for high availability reason, we can keep this subgroup of cluster in a particular zone and other subgroup in a different zone. So the index request. If you are just wondering how you can put a document into the or just a keyword into the cluster, just a curl call will be enough to put the whole of your JSON or whole of your REST code. So the client here is the coordinator who accepts the request and send these requests into a primary node or the primary shards, and the shard is responsible enough to route these requests into a separate replicas or kind of other shards. And here you need to specify the consistency level you want to access, because Elasticsearch uses quorum level consistency. So if you specify only 2 nodes or 2 replicas you need to manage, the primary shards will wait until 2 of your nodes or until 2 of your replicas will acknowledge you the data is committed. So after that, you can search these data from just a kind of another REST API call. Here also the client is responsible enough to route these search requests into a separate shards. So here client will write this search query immediately or the losing query graph, and the node will fetch the shards where the document is or the index is mapped, and then query the results and merge and return back to the user. And the final part of your presentation where Elasticsearch, where we use Elasticsearch. So the first, before I move into the next slide, there's one lady who always comes to our team and asks Tilan about the production errors or the CouchDB production failures like that. So here is the post or what they are exactly look like. So she asks always, can you check the CouchDB errors from last Monday between 1 and 1:05 a.m. And Tilan is right there responsible with these posts. But after we introduce Elasticsearch and Kibana kind of stuff, so we have Logstash and Kibana with Elasticsearch who can cater these kind of problems. And with the regular expression that we are maintaining, the nodes can forward their logs into a Logstash, and with the help of Elasticsearch, you can just query the any kind of errors or the logs from the visualization platform called Kibana, and the API team and DBA team both use this Kibana. And here's some kind of console or the message type, kind of all the terms can be indexed just instance away from Kibana, and the payment guys use Gradle kind of tool just similar to Kibana. And before moving to the next slide, even the master phase, master of DB called Aruna, always have this query like from the lead team, can you delete this slow query from last Sunday night? So how you can search this MySQL performance level type of queries from just right instance away. So Elasticsearch is right there for us. The packet beat with Kibana will help us because they can collect and pass these network packet level data of MySQL performance and push this data to Elasticsearch. Elasticsearch here we use as a storage backend as well, other than indexing backend. So the top flow queries and other most important things of the network packet level data can be captured just in the web. So we are running this packet beat and Kibana in TST2 master DB, and we capture the live packets. So here this most wonderful thing, few months back, actually Mahesh is not aggressive like this before. So look at this now, he is very much calm now. Because in a given hour, this is a very huge task in a real-time kind of platform, in Leapset platform where you need to compare the sales in a given region, in a given distance away in a real time. So to cater this solution, we have come up with this graph model. So every merchant in our production is connected with the kind of edges in the attribute instances called properties to hold image. So our production will be just look like this. They are all connected, and through the architecture from the we use TypeDB as our graph solution, and we use Elasticsearch as our search backend. So the Elasticsearch can cater this, can help this TypeDB to sort and index the vertex entries edges. So you can just traverse the edges that the nodes are connected through Elasticsearch. And so we can push predicates on what we want to Elasticsearch, and Python is responsible enough to get the result through Elasticsearch. And the Cassandra is used here for the backend. So Elasticsearch as the indexing mechanism, query result from Cassandra and return the comparison results. So That's all, folks. And for the summary, we are just here to emphasize the importance of a search and indexing mechanism kind of ElasticSearch and Solr. And the important thing is ElasticSearch is a very simple RESTful API that use the power of Lucene and competitive with Solr. To get a proper understanding, you need to have a good underlying knowledge of data structures and algorithms inside ElasticSearch. So our effort is to convince the message or convey the message of the data structures that they are performing. So you can deep dive into the ElasticSearch and see the magic. So that's all. If you have questions, we are here to ask. We have to answer.